Right, so this is the second video in the series specifically on electric fields. So we've done electricity basics and now we're going to move on to look at Coulomb's law. So Coulomb's law allows you to calculate the force experienced by two electric charges some distance away from each other. It's very similar to Newton's law of gravitation, just a couple of differences that are important. So like Newton's law of gravitation, the force experienced depends on the product of the two charges involved. So we've got Q1 times Q2 here, that's the charge on the first object and the charge on the second object multiplied together, and also, like Newton's law of gravitation, the force depends on the distance between those two charges squared. So it's another 1 on r squared relationship. If you double the distance between the charges, the force goes down by a quarter. The first apparent obvious difference is that the constant is definitely different. So with Newton's law of gravitation, the constant was on the top of the fraction, it was just big G. Here, it's not just one constant, it's 4 pi epsilon naught, or I call it E naught because I'm lazy. So it's 4 pi E naught, where epsilon naught, E naught, is the permittivity of free space, and it's got this number. And the reason for the 4 pi will become apparent probably in another video. So for now we'll just treat that as a constant. The units might strike you as a bit odd. You might not have seen Fs before. Farads, so the unit is in farads per meter. We'll just gloss over that for now and come back to farads more later when we do capacitance. So for now, as long as all your different quantities are in SI units, it should work out fine, and we'll think about them a bit more later. So Coulomb's law, very similar to the law of gravitation, except it's for charges. Now, like the law of gravitation, it applies to point particles, but there's a lot of things we might want to consider that aren't point particles, so we can use the same trick to make it work for spheres that you do with gravitation. That is, if you have a charged sphere, let's say a positively charged sphere, then the field around that, whoops, line wasn't too good, the field around that will be radial, and to anything outside the sphere itself, so to any test particle out here, anyone trying to look at the field out here, that's indistinguishable from a radial field coming from a point particle with the same charge. So that is indistinguishable as long as you're outside the sphere from the field coming from a point particle with the same charge as this sphere. So we can use this trick to allow us to consider point particles and spheres as long as we measure the distance from the center of the sphere. That's where the equivalent point particle would reside. Now there's one other difference compared with gravitation, and that's that the direction of the force depends on the two charges. Gravitation is always attractive, but the electrostatic force can be attractive or repulsive. So let's say we have two charges, positive and negative. If the charges are opposite in sign, so in this case a positive and a negative, then they will attract. So these two charged objects are going to experience an equal and opposite force of attraction because they have opposite signs of their charge. If we swap this one out and replace it with a charged particle with a positive charge, now we've got two charges with a positive charge, they are going to repel. And in this case the repulsion is going to be stronger because this one has twice the charge. And the force, if you remember the formula on the page before, depends on the product of these two charges. This is going to be a repulsion and it's going to be twice as much. That exact same force acts on both of the charges, so it's not like, this force is larger or something because that one's got twice the charge. The force on both of them is the same, as you would see by plugging it into this formula. You know, it doesn't matter which one you consider, all the numbers that go into that formula are the same. So what can we do with this? Well, let's try a couple of examples just to see how you get the hang of it. So question, what's the force acting on an electron in a hydrogen atom? So hydrogen atom, a standard one, usual isotope of hydrogen, has a proton in the middle and an electron going around it. What's the force acting on it? Well, we need to know the charges of the two things, Q1, Q2. Let's write the formula down. F equals Q1, Q2 on 4 pi E naught R squared. We need to know the charges on both of them. That's easy because they both have the charge of an electron. One's positive, one's negative. E naught we've got here. We just need to know the distance between them. Now it's roughly, an atom is roughly 10 to the minus 10 meters across, so the radius is going to be 0.5, let's call it, times 10 to the minus 10 meters across. Now comes the point where you have to put all this into your calculator, and there's a lot of stuff in and a lot of powers of 10 to put in, so it's worth being careful. I might just try and do this on a calculator on the board, just to give you an idea for how much stuff's involved and how careful you need to be. So let's get cracking with the Q1, Q2. Now, since they're both the charge on an electron, I'm just going to square that because I think it's going to make my life easier. So 1.6 E minus 19 squared, because it's E times E over here. This is just E times E, so that's E squared. And then I'm going to divide that by, I might just open up a bracket just to help organise myself, 4 times pi times E naught, 8.85 e to the minus 12 times r squared. Now, I don't know, I'm a brackets fan, so I'm going to put some more brackets in here as well. That's 0.5 times 10 to the minus 10, and that is squared. I just like brackets, me. And then close that final bracket. Hopefully this will give us the right answer. 9.2 times 10 to the minus 8 newtons. Now, I would strongly recommend you check that as well. Have a go at plonking that, all of that into your calculator as well, and see if that's the right answer. If it's not, let me know next lesson and I'll add a comment to this video. That answer is incredibly small as a force, as forces go, but then the electron is also incredibly light, so you'd probably be expecting that force to be small. Okay, so there we have it. That's an example of using Coulomb's law to work out a force. Can we apply this to a more complicated situation? What about if we have more than one charge? More than two charges. Someone brought this up last lesson with masses. What if you had more than two masses? Well, let's say we want to know the force on this one here, this 10 microcoulomb charge. We can just separately add up the forces from the other two charges. So there's going to be a force of repulsion from the green charge, because they're both positive. There's going to be a force of attraction from the red charge, because they have opposite signs. One's positive, one's negative. And then the overall force is going to be the vector sum of those two forces, because forces are vectors. So it's another case of applying the good old formula, F equals Q1 Q2 on 4 pi E naught R squared. So I won't bore you with doing this again on the big calculator, so I'm going to pause it here. I'll do the working out. I suggest you pause it as well and have a quick go at doing the working out, and then we'll see what the answer is. Okay, I've crunched the numbers and I've come up with 0.7 newtons for this force here and 1.8 newtons for this one here. So just to make it look a bit more to scale, I'm going to draw this one longer, because it helps if the diagram is vaguely to scale. So now our resultant force, overall force, is going to be something like that. Now, to find this resultant force, obviously we can use Pythagoras. I'll leave that one up to you. I'm not even going to bother checking that now, but have a go at calculating that, and you could even, without too much difficulty, work out the angle as well of that force. So we can apply Coulomb's law to 2 charges, and it's not that much of a push to apply it to 3 charges. You just have to be careful thinking about the directions the force is going to act, and then add them together as vectors to find the overall resultant. And I think that is it. So have a go now, at the next video, which will be some examples of this.